Second. Opening slide for my keynote presentation. Is that coming up okay?
Yep, it's coming up.
Yeah. Okay. It looks like, yeah, we've got a decent number of people. So yeah, might as well get underway. So yes, for those of you that haven't met or chatted with me before, my name's Reece Thomas. And yes, as you can see, I was a primary candidate back in 2008, getting further and further ago every time I give this tute. So a big disclaimer in there that things may well have changed in that ensuing period. But yes, I also wanted to just share that link, and I'll stick it in the comments at some point as well. Many of you are already aware of it, I know. That yes, I put some of the primary exam resources onto one of my blog posts. And that includes also a link to the slides that I use for these presentations, as well as some of the recordings. Originally audio, but this year it's been Zoom recordings that have made it onto that website. So certainly check that out. And let me know, yes, if there's any issues with the stuff on there, or if you have any suggestions, or if there's things that are no longer relevant that you think I need to change in these tutes. But yes, this week's topic is nutrition and metabolism, which, yes, is not necessarily a core topic for the primary exam, but as we'll kind of see further along, there's some points where it does kind of overlap or have relevance to other topics that are more core. So we'll get to that in due time. But yes, feeling a little bit lazy today, so I think I'll just start with my summary slide, give you the next couple of hours. You can just copy that down, and then there'll be a quiz at the end, and that should just about wrap things up. But no, yes, as you can see, the kind of all this biochemistry and metabolic pathways can be quite overwhelming. When you start digging into it, it can get very convoluted and amazing. But the good news is that for the primary exam, as I said, it's not a massive core topic, and it's really only a relatively small component of all these metabolic pathways that are kind of examinable. And yeah, as I mentioned, there'll be some that are slightly more core than others, and they have relevance both to, yeah, I guess, passing the exam, but also some clinical relevance as well. And also, to try and keep it a bit more interesting, I like to throw in the occasional historical anecdote or story or of how things have developed to try and maintain some interest. So yes, there's another thing I do in my tute. So this is going back to the primary syllabus when I sat it, these useful list of instructional objectives and required abilities. This is the one for nutrition and metabolism. And I've got a link to the whole syllabus as it was when I sat it on that blog site. That can be a useful way to go through and tick off everything that you may or may not have done yet. But again, with that caveat that the syllabus has changed in that time, but a lot of the content is still the same. And yes, I'll try and keep it as interactive as possible. So yes, you might need to kind of take yourself off mute at times to answer questions or interact. So yes, I'll let you know, yeah, kind of see how we go with that, and how good people are at finding the mute button. The other disclaimer that I give for each of my tutes is the whole spherical cow concept. And if you haven't heard the joke before, it's along the lines of: a farmer employs some scientists and engineers to work out the most efficient way to milk cows. They eventually come back with their solution, something along the lines of, let's consider a perfectly elastic spherical cow in a vacuum. And just that idea that often, in order to be able to explain and describe things and to pass exams, we have to grossly oversimplify things. But often, yeah, that's in order to teach the important concepts and provide a grounding to then explore the concepts further if we need to, or if we don't, just enough to get us through the exam. So yes, I thought we'd kick things off today with the concept of metabolic rate. So yes, if anyone wants to jump in at this point and What do we mean by metabolism, and what do we mean by the metabolic rate of a particular organism? And I guess the human is what we're most interested in, but it's pretty generalized. So what is metabolism, and what does metabolic rate mean?
You might have to pick someone out of the list, I think.
Okay, Ben, you're at the top of the list. Maybe, yeah, so yes, maybe I should work out who's just sat the primary, and we can almost run it as a bit of a Viva question.
Yeah, I feel like the bottom of the list always get overlooked. But you can.
Oh, right, yeah. Maybe maybe who wants? We can get Ben to pick up people that are.
Oh no! I don't want to do that. But,
okay, well, I'll just work my way down the list. Ben, you can get us started on this one.
Okay, so I would say metabolic rate is the energy usage that occurs for a person, and it varies with certain factors. So they can be like metabolic they can be sort of things like exercise, endocrine factors like thyroxine levels, fasting state or fed state, and it's the consumption of energy measured in joules.
Mm-hmm. Yep. And I guess, what is it at the molecular level? What is this metabolism that we're talking about?
Oh, we're quantifying cellular respiration.
Right. Yep. Yeah, that's a pretty neat way of putting it. And yes, you're kind of right there. It's the amount of energy liberated per unit time. Actually, what I'll do is I'll kind of, when I'm asking questions, I'll ask them, and then I'll just work my way down the list. So I'm not sure what the list looks like on your computer, but if there's a question that you think you know the answer to, you might want to jump in before I end up asking you one that you have no idea of. So just a word of warning there. So Edward's up next. But anyway, yep, so metabolic rate. And yes, the word kind of... So catabolism literally means, from the Greek or Latin, I'm not sure which, means to throw downward, and anabolism, to throw upward. So that idea of, yes, there's metabolism overall, these cellular respiration and these metabolic activities, but then you can have catabolism that is making of breaking down these substrates, whereas anabolism is kind of building them back up again, and that's where that concept of anabolic steroids comes from, or when we're in a catabolic state, when we're unwell or fasting or post-operatively, those sorts of things. So Ben, I think you might have touched on this before. So yeah, what is it that we're actually measuring? And then I guess, yeah, the next question is, how do we measure it? So Ben, you can follow on from your original question.
So it's a quantification. So we measure it in joules,
Yep.
and the quantification of it is not something which is very easily done, but you can measure oxygen consumption, or you can measure heat production.
Mm-hmm. Yep. So the joules bit, what's that a measure of, a unit of measure of?
So a joule is, and it's similar in the way to a calorie, but I think it's, so a joule is a SI unit for energy.
Mm-hmm.
But the one I can remember is a calorie, which is the amount of energy required to heat 1 gram of water by 1 degree, something like that.
Yes, yep, that's pretty much. And I think, yeah, the other provisor is at atmospheric pressure, because that, of course, affects that. And yeah, so I guess the joule is a measure of energy. How does that, when we talk about a metabolic rate, what other factor do we need to include there?
Body surface area.
I guess, yeah, so often it is measured as in body surface area, but when we're talking about a rate of something, what does rate mean? So it's not just energy, it's energy
over time.
Over time, yeah, that's right. And so what's the unit of measure that we're talking about then?
So I think it's, well, it'd be joules per second, I think, but it might be joules per minute.
Yeah, so I guess I'll ask the question again. So what is the unit of measure there? It doesn't matter. I'm trying to crack a joke. It's watts. So yeah, so metabolic rate is measured in watts, whereas I guess, yes, the which is joules per second, I think, is 1 watt. I think we'll come back to that a bit more later on. And yeah, no, so that's, yeah, it sounds like you've got a pretty good grasp of that sort of stuff, and we'll expand on some of those concepts that you mentioned as we go along. So this formula here is from Ganong, which is one of the recommended texts, or certainly was when I went through, but I think it's still on the list last time I checked. So yes, this kind of provides a good point to think about all the things that we're interested in terms of metabolism and how we measure it, how we can modify it, and how we can understand it. And so this idea of energy output is kind of that's the energy liberated by all the kind of catabolic processes in the body. So as we're breaking these things down, they will liberate energy, because yeah, one of the key things is that all metabolism is kind of inefficient and produces heat. So even when you're kind of going from one substrate, breaking it down into a smaller one, there's going to be some inefficiency in that transition, and that heat will be released as a result. So the energy output is the energy liberated by catabolic processes in the body. Then energy storage, that kind of refers to, I guess, the digesting and metabolizing and storing of food that we eat. So that's one of the elements in it. And then there's the heat element, which, as I said, will sometimes be either a byproduct or a intentional part of metabolism. What about external work? So so it's kind of Ed, Dan, and Phil next on the list. So if one of you, maybe Ed, want to have a crack at, what can you tell me about external work? What's that referring to?
I'm actually not too sure about that.
Anyone else want to have a...
Is it just the actual like physical result? Yeah, like movement or
yep,
result of what you're doing?
Yeah, that's pretty much it. So when we think about work in kind of physics, the idea of that is that it's the force multiplied by the distance that force moves a mass. So that's basically just what work is. And so external work is, yeah, the work that we're doing in kind of moving around. Yes, can you, so I guess it's primarily referring to muscular contraction, but what can you, this is what we'll kind of branch off into, I guess, another part of the primary exam. What can you tell me about muscular contractions? Just thinking skeletal muscle in particular, but I guess it's also relevant for the cardiac muscle. What type of different muscle contractions are you aware of?
So broadly, there's isotonic or isometric contraction.
Yep. What's the difference between those two?
So isotonic refers to alternating contraction and relaxation of muscles. So for and a typical example of that is, you know, aerobic, what we call as aerobic exercise, for example, cycling, running, swimming. Whereas isometric is when the muscle is active, but it's maintaining a constant level of contraction. So such as weight lifting, and then, you know, keeping that weight lifted at the same like constantly, like without changing its position. Yeah.
Yep. Yeah, so kind of the clues in the names of those two things. So iso kind of means same, and then tonic is force. So with an isotonic contraction, you're lifting a weight, you're maintaining the same force, but the length of the muscle is moving. Whereas in isometric, it's the same length. So metric is the length, so it's at the same length, but yeah, and it's kind of holding this kind of fixed force. So yes, it's kind of against a resistance, but it's not actually moving. And so in the context of those two, how does that relate to external work? So thinking about an isotonic contraction.
So that's consistent work throughout, whereas isometric may be variable levels of work depending on how much movement there is.
Yes, and so yeah, I guess in the kind of the spherical cow sense, with an isometric contraction, there's no movement, so there's no external work there. So all of the energy that's utilized for a isometric contraction ultimately appears as heat, whereas for an isotonic contraction, there is some external work. So that needs to be fed into the equation, but it's not 100% efficient, as we said, it's always some inefficiency there. So an isotonic contraction works at a peak efficiency. So the best level of efficiency you can get out of an isotonic contraction is about 50%. So even in that situation, there'll be some of that energy being appearing as heat. And so that's they're the things that kind of make up this energy balance when we're thinking about metabolism and measuring metabolism and things that come into play, which kind of Ben touched on earlier. I'll just check my notes here and see. Yes, so that's right. Yeah, we started talking about units. You mentioned calories, Ben. And yeah, this is where it gets confusing, the different units that get used, because there's kind of different types of calories. There's what they talk about as the gram calorie, and that's the one that you mentioned, Ben, where that's the energy needed to raise 1 gram of water by 1 degree Celsius at 1 atmosphere of pressure. So that's kind of the basic unit. But then when we get to talking about food and labeling on food, they talk about a food calorie. I'm not sure how this came about, but probably for convenience, they talk about, so 1,000 gram calories equals 1 food calorie. And usually the food calorie is designated with a capital C, whereas the gram calorie is the lowercase c.
I get just confused, people calling it kilocalories.
Well, yeah, so that's exactly right. And so this is why the SI units are kind of the SI units for a reason. But yes, this is definitely one area where the SI units haven't kind of really taken over. And so when they talk about a kilocalorie, it's not clear whether they're talking about 1,000 food calories or 1,000 gram calories. But if it's a lowercase k with a uppercase C, then you have to assume that they're talking about 1,000 food calories, but I'm not sure how consistent that is. So yes, you're right. It is definitely a point of confusion. So yes, does anyone know what the conversion is between a gram calorie and a joule, given that joule is the SI units?
I think one calorie is 4.18 joules.
Yep, that's pretty good. So yes, I've got 4.184. But yep, that sounds about right. So yes, a joule, yes, is kind of a smaller unit of energy than the calorie. So yes, it's 1 calorie is 4.184 joules. And yes, we kind of talked about that. Yes, the calorie, it's really just a unit of energy, just like the joule. And we've talked about, yes, that metabolic rate is energy per unit time. And so a watt, which is 1 joule per second, and watt is kind of a measurement of power. So in some ways, metabolic rate is a power. So yes, in that sense, we do literally have the power. But throughout history, theories about the source of this power or this heat energy that humans and other animals have, it's kind of a long and convoluted past. So you go back to the ancient Greeks and Aristotle. So he believed that the heart was the site of innate heat, and that kind of this heat was given to us at birth, and that the reason for breathing was to let out cool the heat of the heart. So that heat needed to get out somehow, and breathing, you breathe out kind of warm air, and that was how we kind of cooled the heat down that came from the heart. Fast forward a bit to the Middle Ages, and they had kind of worked out that some heat was produced by body motion. So that kind of muscular contraction that we were talking about, they were able to work out. I'm not exactly sure how they came to this conclusion, but yes, that I guess the body gets warm after you do exercise. But then they also thought that it was partly caused by the friction of the blood in the blood vessels. There's probably some truth to that, but I suspect it's relatively minor compared to the other sources of this heat or power. that we have. But then it was in the 1600s when a lot of scientific discoveries and process and the whole scientific method was kind of developed that really started to make progress. And one of the initial studies looking at this kind of metabolism and cellular respiration involved an experiment much like this. Now, let's see if this is going to work. Yeah, so here we go. There's not meant to be any sound, but okay, yes, so a pretty short and simple experiment. Yeah, so I gather Dan's next on the list, but if anyone wants to jump in, or Dan, you can jump in. So what's going on here with this little experiment? Can you, yeah, tell me what's the process that's happening here?
This is showing combustion and the consumption of oxygen.
Yep. And why does the floating candle rise?
Oh, I didn't see that bit of it.
Okay, let's see if I can. I'll play it again.
No, I appreciate that now. The candle rises because there's. The candle might rise if it's consumed some oxygen, but it's also spat out some CO2, so I don't think that's it. The temperature might have risen. That would increase any saturation vapor pressure. So I don't know why the water rises.
Anyone else want to? You're certainly on the right track. Yes, I can hear your brain ticking over.
As the oxygen's consumed, it creates a vacuum that pulls the water in.
Yep.
And the CO2 can escape out because it can diffuse into water.
Yes, that's the key point here. That yes, because you're right. Yes, we kind of produce CO2 and the oxygen is consumed, and we'll get to this again in a little bit in kind of pretty comparable amounts. So you wouldn't necessarily expect the pressure to drop inside the beaker. But yes, the key thing is that, and yeah, again, this is another example of this kind of metabolism topic overlapping with a more core topic of respiratory physiology, because that difference in solubility of CO2 versus oxygen is crucial in understanding oxygen transport and how the lungs work and all that sort of thing. And so, yes, you can kind of see it in action with this kind of very basic experiment that you can do at home. And yes, kind of the main compounds involved, oxygen and CO2 there. I'm just checking my notes. Yes, we talked about that. Yeah, so then the next question, and yes, what would happen if instead of a candle, you put a mouse inside underneath that beaker? And Phil, is next on the list, or if someone else wants to jump in?
You put a mouse?
Yeah, a live mouse. And then put the beaker over the top.
It would continue to consume oxygen, but it would have no way of getting rid of the CO2 or getting more oxygen. It would asphyxiate.
Yes, and what would happen in the process compared to what? Yes, like so. Yes, let's say we've got the mouse on a floating platform inside a jar with the water there. Yes, the mouse would die eventually.
I guess the same thing. More water would come in.
Yeah.
And CO2 would leave.
Yeah, so the CO2 would dissolve again, and you'd get the same thing happen. And indeed, that was an experiment that was done in kind of the 1600s by John Mayo, and he was kind of the first one to do this sort of thing. And so yes, he would put a mouse inside a bell jar, inside a thing of water, and he noticed that eventually the mouse would die, but the level of water would kind of rise up as well. And yeah, he also did this same experiment with the candle as well, and kind of noticed that same phenomenon. And also he noticed he put the candle in and a mouse together at the same time. The candle would go out and the mouse would live a little bit longer, but then it too would die. But if he did it without the candle, the mouse would live longer than with the candle in there. So he was kind of able to surmise from that whatever process was going on, it was whatever the candle's doing, the mouse is doing the same thing, but just through a living mechanism rather than a purely chemical, physical mechanism. And so, yeah, as a result of that and some other experiments, he developed a quite detailed and in many aspects correct view of what breathing and respiration was about. He saw muscle contraction as a chemical reaction, which was quite novel at that time. And also, this was quite a new concept, because this showed that kind of air, which for centuries, back to the Greeks, where they thought about fire, wind, earth, and water as the 4 elements. This kind of showed for the first time that air was actually more than one element, that was kind of broken up into these different elements that you could separate out in some sense. But he didn't really get the recognition that he deserved in his own lifetime for various reasons, partly because he died quite young. But some larger names in chemistry and physiology, so Priestley and Lavoisier, who you might have heard in terms of the discovery of oxygen. They got a lot of the credit, but probably, yes, John Mayo had done it kind of a century or more before them. And checking my notes, yes. And so, yes, Lavoisier's experiments, kind of, I'm not sure if he was actually aware of Mayo's stuff. I suspect not. His stuff didn't become more well-known until much more recently. But Lavoisier, instead of using a mouse, he used an actual guinea pig. I'm not sure if this is where the term being a guinea pig in an experiment comes from, but his experiment involving guinea pigs looked differently, but with some similar concepts in there. So this is what he used. So he put a guinea pig in, I'll see if my mouse, yeah. So he put a guinea pig, a live guinea pig in this middle section here. I'm not sure if they were fed or how they were kept alive or just left to their own devices in there. And then the middle chamber, that was all filled with ice. And then the outer chamber was also filled with more ice to kind of, I guess, insulate this inner chamber against the external environment, because they wanted to keep it all as close to 0 degrees as possible through that ice. And then just to make doubly sure they would kind of do it in winter outside, just to kind of try and keep the temperature as stable as possible. So put a guinea pig in there, you've got ice in this middle chamber, and then kind of a device underneath it to catch the water. And so what do you think was kind of happening? What's the basis of this experiment? Does anyone want to have a crack at that? What's going to happen to the ice over time?
It'll melt.
Yep. Okay. And so, yeah, that's pretty much it. Oh, sorry, I've lost my place in the notes. So yeah, so over time, the body heat from the guinea pig will melt the ice around it, and then as you can see through this funnel and valve mechanism, you can then collect the ice and measure it. And yeah, so this was part of his a larger body of work as well, where he came on to develop theories around like I don't know if you've learned about it from the oxygen stuff, they talk about phlogiston and dephlogisticated air, all that sort of stuff, and kind of the development of the theory of oxygen, along with Joseph Priestley. And this was one of the key experiments in that. Now, I guess there's another thing that you can work out here. So the relationship between the heat and the ice melting, does anyone want to expand on what that is? I noticed there's one participant that's removed their name from the profile, so might need to pick on someone else. Yeah, so when you've got heat melting ice in this context, how could we use, what information can we get from that?
Well, you should be able to determine the quantity of ice that is melted,
Yes,
by the water that you collect.
Yep, and then what can you do with that?
You will be able to measure it, and then you can determine how much heat was required to produce that amount of water from ice.
Yeah, so what's that idea called or referred to? What are we talking about there?
Calorimetry.
Yes. So that's the broader concept of measuring metabolic rate, but that conversion of ice into water, what's the term for that? And yeah, the kind of the heat involved.
I guess you could say it's melting, and it's the latent heat of.
Yep.
I don't know.
So where else are you familiar with the
the
idea of latent heat?
usually from a change of state from one to another, say from a solid to a gas, a liquid to a gas, or a solid to a liquid.
Yeah, so that's probably where we're most familiar with the concept of latent heat or latent heat energy of things. So yeah, when we're talking about vaporization, so that's obviously critical to the inhaled agents that we use and how a vaporizer works, and particularly for things like desflurane, where a very low boiling point. But yeah, there's the same principle when you're turning from a solid into a liquid as well. There's, I think it's sometimes called the latent heat of fusion or something, which I don't get where that word fusion comes from. But yes, there is that energy there. And so what can you tell me about this? Why is it called latent? What's the latent aspect of it? And also, I want Annabelle, you're next on my list. If anyone wants to answer what does the latent bit in latent heat refer to, whether it's latent heat of vaporization or latent heat of fusion, melting?
I'm not sure, but is it to do with the fact that it's only a process during vaporization, so at rest? I don't know how to explain it. I'm not really sure, but latent usually means that it's sort of hiding away. Yes,
no, that's right. And so, yeah, I can kind of think I can see where you're going with it. So yes, the whole thing about this latent heat is, and in this example, so you can have ice at 0 degrees Celsius, and you can have water at 0 degrees Celsius. But to go from one to the other, you need to add heat. So normally with the laws of thermodynamics, if you add heat to a system, the temperature goes up. But in these kind of boundary conditions, the transition from one state to another, you add heat to the system, but there's no change in temperature. And that's because the heat is going into breaking the bonds that result in the phase change. And that heat is effectively hidden because I've added heat to the system, but I can't see a rise in temperature. So that's where the idea of latent heat comes from. And all that energy has gone into breaking that bonds, and it has to come from the external environment. And yes, you're able to, for a given substance, measure what that latent heat is. And then the reverse, if it's going in the other direction. So when you have the going from a vapor to a liquid, or from a liquid to a solid, there's energy involved there, and it's the same amount of energy, but it'll be giving off energy rather than absorbing it with those phase changes. So yes, that means then that given that, yeah, you know, and so for example, for ice going to, and this becomes important, actually we'll probably come to that a little bit further on. But yeah, so the value for the latent heat of fusion of water, so a total of 334 joules of energy are required to melt 1 gram of ice at 0 degrees Celsius. And that's called the latent heat of fusion. So therefore, at 0 degrees Celsius, liquid water has 334 joules per gram to the -1 more energy than ice at the same temperature. So that's that latent nature. It's kind of hidden, even though they're at the same temperature. The liquid water has more energy in it than ice at that temperature. And so from then you can work out then, okay, well, we've got how much water melted from the body heat of the guinea pig. So then we can convert that to the amount of energy, and that's basically a proxy for their metabolic rate. And interestingly, they worked out that I think there was, well, I think I've got the numbers here somewhere. So it was, so yes, during the 24 hours of this experiment, apparently, so this is why I'm wondering whether the guinea pig survived the whole time, at 13 ounces or 370 grams of ice melted. And so from that mass of 334 joules of energy per gram of ice, you could then work out that, well, in that 24-hour period, there was 123.58 kilojoules over the day, and then dividing by 24, dividing by 60, dividing by 60, you could estimate the metabolic rate under these conditions of a guinea pig at 1.43 watts, apparently, in case some trivia quiz ever. And I did manage to find somewhere on the internet, someone had measured the basal metabolic rate of a guinea pig, and they came up with 2.13. So it's not exactly the same, but it's certainly not out by orders of magnitude or whatever. So it shows how good they were in these days at measuring these kind of things precisely, which was a key part of that scientific revolution. And yes, he eventually kind of made kind of this statement on the basis of this and many other experiments that breathing is therefore a combustion, in fact, very slow, but moreover perfectly similar to that of coal. And that was quite a revelation that this cellular respiration, this breathing, this heat that we produce at the chemical level is no different to burning coal. You've got fuel source and you've got oxygen. You combine them, it produces heat, and you end up with carbon dioxide. And that's basically at the bare bones what our metabolism is as well. And a strange twist of fate, Lavoisier was actually subsequently beheaded by guillotine in the French Revolution, which tended to happen to smart, rich people back at that time, unfortunately. So yeah, so we've got this idea of metabolism. The body uses fuel and oxygen to produce heat and carbon dioxide. So yes, I guess another core topic that we've kind of touched on briefly is basal metabolic rate. So how is basal metabolic rate different to basal? Who wants to have a crack at that?
I can have a go at that one.
Sure, thanks, Sean.
So basal metabolic rate is the sort of minimum metabolic rate required to sustain life. So it's usually measured under certain conditions. So at rest, at room temperature, at 12 hours after a meal. So you're not getting any contribution from exercise or the metabolic rate from digestion or anything else. It's just the minimum metabolic rate.
When you say room temperature, which room are we talking about? Theta 7 or my nicely heated study at the moment?
I don't have a specific temperature, but I think room temperature is usually, is it 25 or 21 degrees Celsius?
I think they talk about a standard temperature and pressure, or there's a few different ones, but there is a specific term used to describe what the ambient temperature should be in this context that is kind of relevant to that. I think we do need to know about this for the primary. Does anyone else know what I'm thinking? And
is this related to the thermoneutral zone?
Yes, that's right. So yeah, actually maybe we'll come to the, yeah, so you mentioned, yeah, so I think you've kind of got it spot on. So it's the kind of the minimum level of metabolism needed, yeah, at rest to keep us alive. And there's certain conditions that it's measured at. We'll get that to that in a moment. But yes, back to this kind of message. So again, yeah, we're measuring this energy output. And so you mentioned that, yeah, they're kind of at rest. So they're not doing any external work, any external work. As you mentioned, Sean, the kind of postprandial, haven't eaten for a while. So we're not doing any energy storage energy. So that means that all our energy output from our metabolism is only as heat. So that means that you can then use heat as a proxy for a metabolic rate. And if it's satisfied all those other conditions, then it is our basal metabolic rate. And yes, so how is it measured? So you kind of mentioned some of the conditions, but does anyone know that there's a specific name for the device that we use to measure it, depending on, yes, exactly how we're doing it and how accurate we want to be?
Is that calorimetry?
Yep. So there's, yes, two different types of calorimetry. Do you know what they are and the difference between them?
Direct is the measurement of heat production. Mm-hmm. So in an insulated room. Mm-hmm. I don't really know exactly what that looks like beyond that general concept.
Yep.
And then is indirect measuring oxygen consumption?
Yeah. No, that's pretty much it in a nutshell. So yes. now I think, yeah, so the next slide kind of shows the insulated box that gets used. And so this is what's called an Atwater Benedict respiration chamber. Yeah, so this is where and I think, yeah, so I've got so you touched before on the conditions for measuring basal metabolic rate, and this is from the Oxford Handbook of Nutrition and Dietetics. They have a list, and it's probably slightly different depending on which one you read, but it covers the main concept. So they talk about it being in the post-absorptive state, so at least 12 hours since the last meal. And also they tell you to avoid stimulants such as caffeine and smoking. In the thermoneutral zone, which we'll get to in a little bit, you're meant to be supine, which I'm guessing is to, yes, avoid some of that energy from muscle contraction needed to keep you upright. They talk about being awake, but in a state of complete physical and mental relaxation. I'm not sure if I could do that if I'm not allowed to have a coffee beforehand. And then they go on to talk about no heavy physical activity the day before. And yes, it's a bit sexist, this bit, but they talk about being non-pregnant and also depending on the phase of the menstrual cycle as well. But obviously, if you want to measure the basal metabolic rate in someone who's pregnant or menstruating, then you need to include them in the study population. So yes, there's a couple of things in there. So the no heavy physical activity the day before, what's that about? I've realized that the list of names changes depending on who comments. So I might have to kind of open the list up and move down a little bit. So yeah, does anyone want to have a crack at why they tell you not to do any heavy physical activity the day before, not just avoiding activity while you're in the box, but avoiding it the day before?
Is it to do with muscle repair?
Yes, I think that's right. Yeah, so that delayed onset muscle soreness you get kind of a day or two after heavy exercise is, yes, obviously an energy requiring process. And so I think even if it doesn't induce that, and it might not necessarily even need to be repair. It might just be the response to the hypertrophic response to that muscle contraction. You might be building up new muscle. Ideally, that's kind of why a lot of people do exercises or weightlifting, that sort of thing. So there'll be, which is quite interesting that, yes, those metabolic processes after exercise can go on for that long. So I kind of found that interesting that they kind of ask you to avoid that so far in advance. What else was I going to touch on? Yes, no, I think that probably covers most. Yeah, actually, so yeah, what can you tell me about, so avoiding smoking and caffeine? What can you tell me about those two agents? Why would they ask us to avoid those?
Both of them are stimulants, which will increase your metabolic turnover.
Yeah, yep, that's pretty much it. And you know, yes, I guess, given it's an anesthetic exam, caffeine's always important to an anaesthetist. So what can you tell me about the mechanism of action of caffeine? Does anyone, I don't think this is actually part of the exam, but it's just a point of interest. Again, a trivia pub quiz night. Does anyone know how caffeine works?
Non-specific phosphodiesterase inhibitor.
Yeah, spot on. And so, yeah, what's the downstream effect of that?
Increases the intracellular calcium, so the force of contractility in muscles. Potentially, it also kicks out more noradrenaline into the nerve terminals.
Okay, yeah, well done. You've skipped a couple of steps there. So what can you tell me about phosphodiesterase?
Phosphodiesterase usually breaks down cyclic AMP.
Right, okay. So its inhibition by caffeine results in more cyclic AMP, and then all the second messengers go down from that. So I did the cellular physiology shoot, which touched on that a bit, and I'll probably touch on it again a little bit in the endocrine shoot, which I think I've got in a few weeks' time as well. But yes, that's pretty good summary there. I think yes, so that's the Atwater Benedict respiration chamber. They're the conditions there, as mentioned before. And so, yes, so these conditions mean that no energy is being consumed in external work or storing energy. So all the energy consumption is converted to heat. Now I'm not sure how well this is showing up on your individual screens, obviously. Now, how clearly can you see the setup, that diagram of what's going on in the box? And what are the key things about the way the box is set up that you can see from the diagrams and the labels?
On-demand oxygen, or is it just pumping it in?
I think it's just replenishing. Well, yes, that's a good. I'm not sure exactly the mechanism for replenishing the oxygen, but yes, I guess the key point is there that it's kind of an airtight box. So the same thing will happen to the subject as happened to the mouse and the candle if they don't put more oxygen in. So yes, there's some way of adding oxygen. So that's kind of important because oxygen, as we've discussed, oxygen will be consumed. What are the other things that are going on that we're interested in and need to deal with? And yes, that's not clearly thing. So that thing above his head with that liquid going through, that's kind of a heat exchanger, and that's how they measure the temperature. So it's again measuring the change in temperature of the water that's kind of being piped through the room. I don't know the specifics of how all that happens. So we've talked about oxygen, we've talked about heat and measuring that. What's the other thing we're interested in?
CO2.
CO2, yeah. So what's dealing with that?
So there's a circuit that allows CO2 to be removed, and there's a pump that ensures there's a unidirectional flow of the CO2, and it's absorbed via the soda lime. Yeah. Not sure what the sulfuric acid is there.
Yeah, well, yeah. So in last year's tube, someone asked that question, and I had no idea, so I looked it up. Does anyone have any suggestions as to?
Maybe it's a weak buffering system, but then I don't know. Why would you need it there if you've got the soda lime anyway?
Yes, yep. So you're right. So the soda limes for the CO2. So I guess yes. What can you tell me about the products of this cellular respiration that we're talking about, and also about the reaction involved in CO2 absorption via soda lime? This is kind of a relevant question to, yes, anesthetic circuits, but also, yes, the cellular physiology that we're talking about here. What's the other byproduct that we haven't really talked about much so far, but kind of will become relevant? And water, yes. So, yes, so both cellular respiration, the end product is water. And so, yes, we kind of humidify air and breathe out humidified air, even though we breathe in dry air. So that produces water, and then yes, the soda lime reaction with carbon dioxide also produces water. So the sulfuric acid is to remove the moisture from the air, to kind of dry out the air again. Otherwise it would get there'd be a lot of condensation in that room over time, as you can imagine.
But how do they get rid of the heat from the soda lime reaction?
That's a good question, actually. I don't know what number 10 is, if that has something to do with it. There might be some regulator there to make sure that, yes, because that's an important point, actually, because you don't want to be artificially, they might need to, I guess they're going to be, one of the conditions is a thermoneutral zone. So they're going to have to regulate the room's temperature. So I suspect the air that's being pumped in, and maybe I should find the original source, and I wouldn't be surprised if number 10 has something to do with temperature, although I guess, oxygen comes in downstream of that, so that would have an impact on temperature as well. But yes, you're right, they would definitely need to allow for that. That's a good point. So yes, I think oh no, maybe we don't get to it quite yet. Any more questions on the Atwater Benedict chamber before we move on? And that whole concept of basal metabolic rate. And so, yes, then once you've determined what the heat production is in that state, you can then do those conversions again, which I think I might come on to that in a little bit as well. And so, yeah, this is from Ganong again. One of the recommended texts. So this is their list of factors affecting the metabolic rate. And so, yes, there's obviously reasons why you might want to measure the metabolic rate in these different states. But I guess the key distinction is that the basal metabolic rate, you need to control for all these things or remove them as much as possible. And then you can then compare it like with other states to see, well, how does that affect the metabolic rate? How much extra energy do we need to do to be able to do that thing, whether it's eating something or doing exercise, or if we're lactating and those sorts of things. But that's just a list from Ganong, which is one of the recommended texts. So I thought I'd throw that in. And so, yeah, so next, the thermoneutral zone, we've kind of touched on it already. So does anyone want to, yeah, this is one of the requirements, measuring the basal metabolic rate. So what can you tell me about the thermoneutral zone? We've got a...
So, oh, sorry.
Oh, no, you go on.
Yep. So the thermoneutral zone is the ambient or environmental temperature where the body can make or has no metabolic, it's at its lowest metabolic rate. And can adjust its core temperature using autonomic changes alone.
Yeah, yep, no, yes, yes, that's pretty good. Definitely got most of it there. And yes, you kind of touched on that already. So yeah, why is it that they want you at the thermoneutral zone for measuring the basal metabolic rate?
Yes, because that's where there will be sort of minimal metabolic rate, or the lowest metabolic rate. Yeah.
So yes, so yeah, and I wasn't sure where in the syllabus this pops up. I don't think it's explicitly mentioned in this topic list, but it's certainly relevant for heat management in feeders. And so yes, it's kind of there. I think the definition I have, I'm not sure where I have got it from. But yes, the thermoneutral zone is defined as the range of ambient temperatures. So it's, yeah, that's important. It's not just one temperature. There's a bit of a range there, and it's key that it's the ambient temperature, because I think I used to get it mixed up with, I think it was the interthreshold range or something, which is body temperatures, a range of body temperatures, whereas the thermoneutral zone is the ambient temperature. So the thermoneutral zone is defined as the range of ambient temperatures where the body can maintain its core temperature solely through regulating dry heat loss, i.e. skin blood flow. So that's what you said, just through those kind of autonomic regulations. But I guess a caveat to that is, so yeah, so it doesn't involve sweating, doesn't involve shivering, and there's no change from resting metabolic rate. So I think the next slide kind of shows that again. Yeah, so you can see there the thermoneutral zone and either side of that. So the body temperature on the left side, kind of as you move far enough away from that and spend a longer time there, your body temperature will drop or will become hypothermic at the other range. But yes, interestingly, the metabolic rate is lowest within that thermoneutral zone. So can you explain, I guess, yeah, we've kind of touched on it already. What is it that's happening outside the thermoneutral zone that makes your metabolic rate kind of go up in both directions? It doesn't just kind of continue. Yeah, what is it that's happening either side of the thermoneutral zone that's increasing metabolic rate?
We have sweating on the right and shivering, and then non-shivering thermogenesis.
All right. Yep. So yeah, that's and yeah, I guess there's a number of things that go on. So certainly for hypothermia, yeah, shivering is going to be a big one that increases your metabolic rate. On the right side, yeah, there'll be vasodilation, there'll be sweating, and other things. And also the other thing is that, I guess, as things get warmer and your body temperature gets warmer, so all those chemical reactions, so generally speaking, chemical reactions happen faster when the ambient temperature is higher. And so, yes, just your normal metabolism will get faster anyway as your body temperature increases. So that would be another possible reason for the increase in metabolic rate above that. But yes, not everyone has room for an Atwater Benedict chamber. So what's a simpler alternative to doing that that form of measurement? And we've kind of touched on it already again. We've got a
consumption.
Sorry?
Oxygen consumption.
Yeah, and what's the term for that?
Indirect calorimetry.
So yeah, so I didn't quite hear that. Probably indirect calorimetry. Also, yeah, so there's someone with no name there. There's a student ID number. Simon Ellis is it, and someone with R. Where are you guys up to in your exam prep? Just trying to get a feel for everybody's stage of study.
Julian and I, sorry, it's going to echo. Julian and I are going to sit the primary next year, so we're just BT, started BT.
Right. Okay. Yep. And who's 600956362?
Oh, we're all the same person because we have audio.
Oh, right. Okay. Okay. That's right. Well, yes. Yeah. Obviously, feel free to jump in at any time. So yes, indirect calorimetry. What can you tell me about this? Yeah, we talked about it's measuring oxygen consumption. So yes, what does it look like compared to the Benedict Roth, the Atwater Benedict chamber? Sorry, I've given you a clue there. So I guess what's the equipment and what's the what are the principles that we're using by measuring the oxygen consumption?
So indirect calorimetry is measuring the oxygen consumption based on the assumption that O2 consumption is proportional to heat and energy output.
Yep, that's pretty much it, yes. And you know what the device looks like? Or I mean, there's a few devices.
Oh, I'm so sorry, we can't hear you again. Hold on.
Okay. All right, we're good now.
Okay. Yes, so yeah, that proportional relationship between oxygen consumption and metabolic rate. And do you know what the devices that can be used? Do you know anything about them or the?
I've got some of them on a page in front of me.
All right, yeah. Isn't there? I think there's some whiteboard feature where we should be able to get you to draw them. But yes, so what? Yes, how are we developing that proportional relationship between oxygen consumption and metabolic rates? So what's the basis of that relationship? It's possibly a bit of game of guess what I'm thinking.
So I think there's a amount of kilocalories proportional to a litre of consumed oxygen. And aside from that, I'm not sure.
Yeah. So I guess, yeah, what are the other, so we're talking about, yeah, this metabolic process of respiration, of burning stuff and producing that heat energy. What are the other, I guess, yeah, so energy production can be calculated by measuring the end products of this, what they call biologic oxidation. So what are the end products that we're interested in? We've kind of already touched on this. So yeah, we're obviously interested in we're consuming oxygen. What are the other things that are produced, I guess? So produced heat, we've talked about.
And the R value.
So the CO2, yes, we'll come to the R value. So there's CO2, we've talked about heat, which we've already said you can measure in the Benedict Atwater chamber. Mentioned CO2. What else gets produced?
Water.
Water, yes. And then there's another thing that's a little bit left of field. So what about if we're burning proteins, which we tend to do, and amino acids? What are the, so there's kind of nitrogenous end products that, because yes, proteins and amino acids don't go to complete oxidation. So we need to take them into account. Now, of those, yes, kind of CO2. So we've talked about measuring heat, but that's hard to do reliably and accurately without that special chamber. CO2, water, and end products of protein catabolism are also tricky to measure in some respects in those absolute senses, whereas oxygen, on the other hand, is comparatively easy to measure. So it's not really stored to any great extent, except when an O2 debt is being incurred. So when you're doing heavy physical activity. But generally speaking, the amount of O2 consumption per unit of time is proportionate to the energy liberated by metabolism. So that, yes, unless you're doing, that really strenuous physical exercise where you're using up more oxygen than you're breathing in, there's a pretty good proportionate relationship between O2 consumption and the energy liberated by metabolism. And then, yes, you could go on to experimentally quantify what that relationship looks like. And so, yes, I guess this is I think, again, this is from Ganong. So this kind of demonstrates, I'm not sure how regularly, if ever, this particular device is, the Benedict Roth spirometer that's kind of been modified a bit. And so this is certainly how it was kind of done early on. So I don't know if this is familiar to any of you. There's the Benedict Roth spirometer can just be used for measuring lung volumes and those sorts of things. But does anyone want to describe kind of what the setup is here and what it's doing and the principles behind it? You can probably read the text to give you some indication, but yes, just looking at the diagram and seeing all the components. And so, yes.
I think what we're seeing is the volume of the breathing chamber reducing as we consume oxygen.
Right. Yeah. So the key thing here is that unlike the Benedict Atwater chamber, where they were adding in new oxygen, this is a closed circuit, completely closed. So while the test is going on, no new oxygen is being added to it. They're consuming the oxygen reservoir in that thing labeled the breathing chamber there. So you've still got a CO2 absorber to get rid of that, so it's not replenishing the volume in that breathing chamber. And then, yes, this kind of bit hard to see, but this water seal, it's kind of, there's some good videos online that kind of show it in action. So this breathing chamber is floating in this bucket of water, effectively upside down. And as the person's attached to the mouthpiece and breathing in and out, there's these one-way check valves here to ensure that the flow is only going in the one direction, like we have on our anesthetic circuits. And yes, with each breath, a bit of O2 is consumed, so that breathing chamber gets smaller and smaller, and kind of that then through all these convoluted pulley mechanisms and this rotating drum so each of that kind of up and down is a breath in and out. And you can then measure that that line from A to B. The slope of that is proportionate to the O2 consumption, and then there'll be charts you can look at, and it all depend on body weight and surface area and all those sorts of things. So that's kind of the old school way of doing it. And then, yes, there's more modern versions where it's all kind of computerized and those sorts of things. And so that makes it a bit simpler again. And then again, you can kind of try and approximate that resting state again with thermoneutral zone, lying down, not doing any activity, fasted if you're having a crack at estimating the basal metabolic rate. But then again, this technique is often used in sports science and athletic stuff, looking at the oxygen consumption during exercise or specific activities to see how they vary. And certainly with this electronic equipment, that's become much easier over time. And then I think someone's already touched on it already. So another concept related to all this CO2 production, oxygen consumption, and metabolic rate and burning of fuel is the respiratory quotient. So who wants to have a crack at kind of, I guess, defining that, and then we can go from there.
And so the respiratory quotient is the ratio of the amount of CO2 produced compared to the amount of oxygen consumed per unit time at a steady state at equilibrium.
Yep. Okay. And what affects the respiratory quotient? So what is it kind of a measure of in some sense?
It's determined by whether you're using carbohydrates, proteins, or lipids.
Yep. And why is that the case? Why do they differ?
If you break down a carbohydrate, each oxygen consumed produces 1 carbon dioxide, just based on the structure of the carbohydrate.
Mm-hmm. Yep.
That ratio is different for protein and lipids.
Yes. Yeah. No, that pretty much nails it. And so yes. And yeah, and I guess this is, yes, an example of why. So in terms of the indirect calorimetry, so the oxygen consumption is a more reliable measure of metabolic rate than CO2 production because of this issue of the respiratory quotient and the source of the energy that is being used in that metabolic process while you're being measured at. And I think I've got a slide here. Just let me have a look. Yes, so this is again from Ganong as well. So yes, so the key thing about carbohydrates is that the carbohydrate molecule, so in this one it's a hexose, glucose, the ratio of the hydrogen and the oxygen are in the same ratio as water. So so the hydrogen and oxygen in the carbohydrate, they kind of make up, not directly, there's a whole long process between them, which we'll come to, but ultimately the hydrogen and oxygen kind of balance the equation is going directly to water. So that means it's just the 6 carbon atoms get turned into 6 carbon dioxide with the 6 oxygen there. So there's that direct kind of one-to-one relationship. Whereas in this particular example of fat, and it will differ depending on whether it's on what lipid it is and whether it's a saturated or unsaturated fatty acid, those sorts of things, showing that yes, there's the ratio of hydrogen and oxygen are much different to carbohydrate, and then it gets even messier with protein. So the respiratory quotient for carbohydrates is 1. For fat, they estimate it to be about 0.7. And for proteins, about 0.8, and a mixed average diet is also about 0.8. But yes, I think it'll vary a bit depending on whether you're in a state of excess or famine, and also insulin sensitivity and other metabolic aspects. But yes, they're kind of the ballpark figures that I have. Now, the interesting thing that you can do with this is, so this is usually the respiratory quotient is talking about stuff at the whole body level, but you can also break it down to look at specific organs. So on the basis of what we've just looked at, what would be the respiratory quotient of the brain? And I think it has been done in some experimental settings, probably not with humans, but yeah, if you could isolate the brain and work out its respiratory quotient, what do you think it would be?
Would it not just be 1?
Yes, why do you say that?
Because the brain uses glucose preferentially for metabolism. And so
yeah, that's pretty much it. So it's certainly preferentially uses glucose. You can, if you get into it, there's some metabolism of ketone bodies, I think, under certain circumstances. And so yes, I think experimentally the respiratory quotient of the brain is about 0.97 to 0.99. Now, another question is from it, and I don't know if any of you use the Kerry Brandis Viva book. That was certainly heavily used when I was going through and found it very good. At the back of that book, there's a whole list of just kind of short, simple question answer things. And this is one of the questions. I think this is where it was from anyway. But do you know there's one organ, or at least one, probably only one actually, that one organ that has a negative respiratory quotient? Do you know what that is? And what does a negative respiratory quotient even mean?
Is it the lungs spitting out more CO2?
So yeah, that someone's given that answer before, and I can see why it makes sense. But I think the respiratory quotient is more about the production of CO2 rather than its elimination. So yes, I think I don't think that would quite fit into the definition of a respiratory quotient, but yes.
Could it? Sorry.
Yeah, go on.
I was going to say red blood cell, but I don't know if that's right.
Oh yeah, so the red blood cell's a bit complicated because it doesn't have a nucleus or mitochondria or anything like that. But no, that's not the one. But yeah, I can see why you might be thinking about that in terms of the binding of oxygen and CO2 there. But what like when we talk about respiratory quotient, what would the fact that it's a negative respiratory quotient actually mean?
I would suggest maybe it's the liver, because it's predominantly, like, it's involved predominantly in anabolism rather than, say, catabolism, potentially.
All right. Yes, it's yeah, I can see where you're getting from, but that's not correct. So
yeah,
we're so yeah, we're talking about so normally we're talking about its production of CO2 and consumption of oxygen. So for it to go negative, one of those two things needs to be flipped. And so in the example I'm thinking of, it's instead of producing CO2, this organ consumes CO2, actually takes it up rather than spits it out. So does that give you any clues as to, yeah, can you think of an organ in the body that actually, where the arterial level of CO2 to that organ would be higher than the venous CO2 leaving that organ? You need to, yes, it's a bit of a, you need to think about
The placenta?
Fetus? No.
I'd need to think about that one, and whether the fetus. Yeah, I'm not. That's not the answer that I have in my head. I'll need to think about that more.
It's not the stomach, is it?
And I guess again, the fetuses and the placenta is probably a bit like the lungs in that it's not really producing or consuming CO2. It's just transferring it and eliminating it. But no, this is an organ where it's an actual chemical reaction that uses CO2 and produces another different product. It's a chemical reaction with CO2. What was the other one that someone said?
I said the stomach.
Yes. Why would that be the case?
I was just thinking of that little diagram where CO2 and then it's changed over to bicarb through carbonic anhydrase, and then you produce hydrogen ions which get excreted into the stomach.
Yeah, no, that's exactly right. So yes, so CO2, you put it in water, it kind of makes that water acidic, yeah, through that kind of process. And yeah, so a core part of producing the hydrochloric acid, effectively, that's in our stomach, is the consumption of CO2. So technically speaking, the stomach has a negative respiratory quotient. And again, I don't know that you'd get asked in the exam. It might come up at the end of a Viva question if you're doing well, but it's a good one for anaesthetic trivia night at some point. Now, at this point, it's kind of an hour in. Might just have a couple of minutes break if you need to go to the toilet, get a coffee or a drink of water. Now, while you're doing that, you can think about this. So this was a question that I got at the end of one of my physiology Viva sections back in the day when they split them into Phys and Pharm. And I think I must have been doing well in the Viva because this kind of came up at the end and I didn't really have time to answer it before the bell rang, thank goodness. But I think it was started off as a question on liver physiology. And I'm not too sure how we probably got into some kind of nutritional metabolism thing. And they asked me the question about what would be the preferred diet in terms of respiratory quotient, that sort of thing, for a patient with COPD. So take a couple of minutes, have a drink, get a quick cup of coffee, go to the toilet, and see if you can think about what may or may not be beneficial in terms of respiratory quotients for COPD patients. Okay, chat to you in a couple of minutes. Okay, how's everyone going? Is everyone back? What are people's thoughts on what should we feed people with COPD? Oh, can anyone hear me? Is someone on mute?
We can hear you.
Yep.
I think the answer is you feed them fat so that they produce less CO2 per oxygen consumed.
Yes, I think when I had a look at it afterwards, that was kind of, and I'm not sure how strong the evidence is or whether they actually do this in practice. I can't necessarily remember it happening, but yes, I think that's probably the answer that they were looking for. But yeah, as I said, I kind of ran out of time, thank goodness, because I certainly didn't know that at the time. But yes, I think that's what they're getting to that. So for the given energy density or the amount of calories you're getting from the food, you'll produce less CO2 if it's kind of predominantly a fat diet, and then therefore, yeah, kind of less need to reducing the CO2 load and work of breathing and all that sort of stuff for patients with COPD. So yes, again, that wasn't a standard. I think I must have been doing well in that particular section of the Viva for them to kind of get to the bottom of the barrel like that. Okay, any other questions at this point? Before we move on. I'll take that as a no. So, but we'll continue on hang on a second, I'm just checking my notes here. Yeah, no, that's did cover that. Yeah, okay, so staying on the topic of food for now. So yes, I don't know if you've heard of this concept. So what can you tell me about this idea? Have you heard of negative calories? What does it mean? What's it getting at? And it's related to, we kind of touched on it a bit before, by why do you need to be fasted when measuring the basal metabolic rate as well, kind of related to that. Have you heard of the idea of negative calories?
Sorry, I just got back. I was going to say, is it?
Oh, sorry.
So is it something that consumes more calories than it contains in the process of eating it?
That's pretty much it. Yeah. So, and yeah, this is kind of, comes back to that idea of why you need to be fasted when measuring the basal metabolic rate, that just the digestion and storage of food from that equation that we had from Ganong about that energy, food storage, that increases your metabolic rate. And so they, actually we'll come to it. And yeah, so yeah, it's that idea of the consumption and storage, digestion of the food takes up more calories than the food, what the food itself gives you. And so the technical term for this, I don't really know where it came from or why it's this rather than something else, but they talk about the specific dynamic action is the term used to describe I think what they call the obligatory energy expenditure that occurs during the food's assimilation into the body. So this specific dynamic action, I think it does have some other names. So the thermic effect of food. So when you eat food, your metabolic rate increases and generates heat. Or they talk about dietary induced thermogenesis. So again, you eat something and it induces a thermogenesis. Your metabolic rate goes up, and I think there's lots of theories as to why that might be the case, but it's still not entirely clear. I don't think they've completely solved where all the increased metabolism comes from, but it's not hard to imagine some examples of where it would come from in terms of producing saliva, the act of chewing, act of swallowing, production of acid, or the enzymes for digestion, gut motility, those sorts of things. You can easily imagine them using up energy and increasing your metabolic rate. And I think this is very, very fine print stuff. I don't think you'd need to know much about this, except in the context of how it affects your basal metabolic rate and why you need to be fasted when you're measuring that. But yeah, so there are some numbers that kind of worked out for different food types. As you can imagine, there would be different values of this specific dynamic action. So for carbohydrates, they reckon it's a bit, depending on the carbohydrate, 5 to 15% of the energy that's consumed. So the vast majority of it is kind of available, it's not consumed. Protein seems to be the hardest one to digest in this context. So it's as much as 20 to 35% of the calorie content of the food is used up just ingesting and processing it. Whereas fats is pretty similar to carbohydrates, 5 to 15%. And yes, things like celery, I think I've heard it for watermelon, lettuce, and other things like that are often touted as being negative calories because the majority of it's water. But apparently there was some study that had the specific dynamic action of celery at only 8%. So it's actually quite low. So even just eating celery, you're still going to put on weight. But at the same time, it's not very energy dense. So to get any decent calories out of celery, you need to eat a massive truck full of it. And it will also get complicated. They can probably work out the specific dynamic action for individual foods, just eaten alone. But once you lump them all together in a meal, it's going to get a lot more complicated because then you're kind of chewing it all together, you're digesting it all together. There might be a fixed amount of enzymes that get secreted, whether you're chewing celery or chewing a lamb roast. So it does get a bit more complicated like most things. But yes, in this context of negative calories, you can start thinking about other options. So we talked before about coffee being a stimulant effect and increasing your basal metabolic rate. So yeah, I guess it could be a potential negative calories thing. But what would be a major confounder to coffee having a negative caloric effect? How do you have your coffee?
So milk and sugar, probably.
Yeah, that's right. So that's the orange mocha frappuccino is not going to have negative calories, no matter how much coffee's in it. But certainly, yeah, we talked a bit before about the amount of energy needed to heat kind of 1 gram of water, 1 degree, and kind of the calories on that sort of thing. So I think that if you're trying to lose weight, then the best way to have your coffee is a cold drip. Black coffee, no milk. So you'll get the caffeine, and then you'll also need to heat it up to your body temperature. So you'll be chewing through the calories in no time, but it's not as easy as that. So I think someone's done the sums, and so we talk about, so I think it was, that conversion of ice to water. And then, of course, not just that latent heat of melting, but then getting it up to your body temperature is going to require some additional energy. But apparently you can burn 37 kilocalories if you eat 1 kilogram of ice. And that's 155 kilojoules using that conversion. So for comparison, 1 gram of Cadbury's dairy milk contains 255 kilojoules. So even with a kilogram of ice, you're barely even going to get half a gram of Cadbury's dairy milk chocolate. So, and I think having much more ice than that's going to cause other issues that you don't want. So yeah, stick to the cold drip, I think, if you're going to do that. The other thing is chewing gum, particularly sugar-free chewing gum. You're going to stimulate salivary production. You're going to have that active chewing. You're probably going to produce some acid in the stomach as well. So probably chewing sugar-free gum is going to help you lose some calories as well. So cold drip and extra, that's the recipe. Okay, so we've eaten this food, and now we're kind of metabolizing it. So looking closer at these pathways that generating all this heat that we've been measuring and producing all this carbon dioxide and using up all this oxygen in various ways. So what can you tell me about, what are some metabolic pathways that you've heard of or that you know of? We'll go kind of create a bit of a list, and we'll go through some of them, and some are more central, some are definitely fine print.
So do you mean like intracellular ones, like glycolysis?
Yes. So that's probably an important one. Yes, talking intracellular rather than kind of in the gut, I guess. So what are some of these intracellular metabolic pathways?
Yeah, so glycolysis, which is the into eventually pyruvate, and then pyruvate becomes acetyl-CoA, and then that's necessary for the Krebs cycle.
Okay, because we'll go through some of these in a bit more detail. Let's just kind of make a bit of a list and begin to say, glycolysis is definitely one, and that's possibly the one that we need to know a bit about. Yeah, what are some other? So yes, so got glycolysis. Then what other ones?
So gluconeogenesis.
Yep.
Glycogen synthesis.
Yep.
And then the reverse of that, so glycogenolysis.
Yep. Those two are pretty fine print. We probably won't go into them today.
Yeah. And so that's for carbohydrates. And then for lipids, there's beta oxidation, lipolysis, and protein synthesis.
Yep. And then what about downstream of those ones?
Downstream of those ones.
So what happens after glycolysis, after beta oxidation, those sorts of things? If we're talking about, kind of going right through that metabolic process and ending up with the CO2 and water that we're talking about, what are some other metabolic processes that need to happen?
Oxygen transport chain?
Yeah, so Phil was just mentioning the electron transport chain.
Yes. What's the other?
Mitochondria.
Yep.
So oxidative phosphorylation.
Yep, so that's a big one. We'll certainly cover that.
Yeah.
There's a step between, so let's talk about glycolysis. Yeah. What happens between glycolysis and oxidative phosphorylation?
Yeah, so I think I was jumping ahead before with it, the Krebs cycle.
Yep. Citric acid cycle, tricyclic acid. Yes, there's a few names for the Krebs cycle. Yeah, that's a big one. I think that's probably the main ones for now. There's some other ones that we'll come to as well. But yes, to kick things off, have a look at this. Does anyone know what this molecule is? It's kind of a key molecule that kind of ties a lot of these metabolic processes together and has a role in numerous other processes in the body that we need to know about, and some more directly relevant to anesthetics than others. Someone's already mentioned it.
Acetylcholine.
Acetyl-CoA, yes. It's so this little bit here, carbon, and then the double bond on oxygen, that's the acetyl bit. The rest of this whole long thing is the CoA bit. So while the CoA bit is the shortest bit of the word, it's the longest bit of the molecule. You certainly don't need to recognize or draw this one. But I just wanted to start off with, because you'll see as we kind of go down these metabolic processes that acetyl-CoA will keep coming up again and again. And if you were at my cellular physiology tute a few months back, yeah, you'll kind of have seen that already. But yes, just for interest's sake, that's the molecule that we'll be dealing with along the way. And so yes, we'll kick off then first of all with glycolysis. Who wants to have a crack at telling me a bit about glycolysis?
So glycolysis is the conversion of glucose into pyruvate, and you also produce 2 ATP products, molecules in the presence of oxygen. Mm-hmm. And it can also go down in the absence of oxygen, can go down the anaerobic pathway to produce lactate.
Yeah. So yes, it's I guess yes. There's probably you can talk about aerobic and anaerobic glycolysis, but I guess in both those situations, normally the process of glycolysis stops at the pyruvate, and then whether it's aerobic or anaerobic is that then what happens to the pyruvate, I guess, and also it does come into that factoring of the net production of things. But yes, I guess the main things, I know I've got a diagram here that shows it all pretty well. So yes, you're starting with glucose here and ending up with pyruvate down here. Now, I guess there's a number of key points to draw out here that, and again, I don't think this is going to be a major core topic for the primary exam. There might be some multiple choice questions on it from memory. But yes, the key things, so it starts with glucose. It's a 6 carbon molecule. And the key thing is that it gets split into 2 things about halfway through, into 2 identical 3 carbon chain molecules. And so 1 molecule of glucose ends up with 2 molecules of pyruvate at the end of glycolysis. So that's one key thing to remember. You can see the other thing is that there's these red lines here that are, for all intents and purposes, unidirectional reactions. So yes, it's that enzyme can only go in that one direction, whereas these ones are bidirectional. So they're kind of reversible reactions. And then the other thing that it's worth pointing out, so you kind of mentioned that 2 ATP was produced, and that's the net production. But I guess, you can break it down into so in the, there's an official term for it, but in this early stages, you're actually consuming ATP to get it through these early processes. But then you kind of regain that ATP further on. So you've actually, from 1 glucose molecule, you consume 2 ATP initially. Then after it gets split into the 2 separate molecules, each of those molecules then produces 2 ATP molecules each. So it's produced 4, consumed 2, so you get that net value of 2. Now, what's the other thing that gets produced during glycolysis that's important that we're interested in?
NADH is produced for the electron chain transfer.
Yeah, that's right. So it's kind of produced here, and I guess, yes, probably come to it again in a little bit. This is where that question of aerobic or anaerobic glycolysis comes in, and the role of lactate and other processes like that. But yeah, so you're right. So as well as the ATP being produced, you also get, again, it's after it's split into the 3 carbon molecules. So you end up, for each molecule of glucose, you get 2 of these NADH molecules. And then there's a side branch to this process of glycolysis that is also, well, we kind of need to know about it in some sense. Does anyone know what it is I'm thinking of and trying to get you to guess? So there's a alternative pathway in some.
How about the hexose monophosphate shunt?
No, so I think that's a separate one further up here.
Or the offshoot for producing 2,3-DPG?
Yes, that's the one I was trying to get you to guess. So, yeah, well done.
That's the Rappaport Lubric shunt or something.
Yes, that's the one. It's got a couple of different names. And so, yes, it happens here. So you can see here this 1,3 bisphosphoglycerate gets converted to 3-phosphoglycerate here, but there's an alternative pathway that this 1,3 bisphosphoglycerate can go through, and I think it's on the next slide. Yes, so this is the a side branch here, the Rappaport Lubric, or it's here on Wiki, it's the Lubric Rappaport pathway, but yeah, it's got a few different names, which I don't know that you necessarily need to know for the exam. But yes, what's the importance of this kind of side branch? What's this molecule here also called?
2,3-DPG.
Yep, that's right. And so what's that used for, Annabelle?
So I thought it was a byproduct in red blood cell metabolism.
Yes, no, you're exactly right. Yep.
Yeah, and it helps to sort of make a conformational change in the is it the globin? I can't remember, some part of the hemoglobin molecule, so that it makes it easier to offload oxygen.
Yeah, so
it reduces the oxygen binding affinity of the hemoglobin molecule.
Yes, I'll have to trust you on which way it does it. That's but no, yeah, that's definitely. So this is, I guess, another example of where this non-core topic of nutrition and metabolism feeds into the more core topic of respiratory physiology and oxygen transport and those sorts of things that you definitely do need to know about. So yes, this molecule, so 2,3-diphosphoglycerate. So sometimes I think it's just weird Greek or Latin. Sometimes, so bis and di kind of mean the same thing. I don't know why they kind of have both options, but this 2,3-DPG that's produced here is that very same molecule that gets used with hemoglobin. And yes, your comment about red blood cells is correct, because this enzyme here, the bisphosphoglycerate mutase, and I'm assuming this one here as well, are only expressed or available in red blood cells. And also in the placenta, I think, is a more recent discovery. So yes, because it's the red blood cells that need this 2,3-bisphosphoglycerate. So it's really the only place that this side branch happens. And what else do you notice about this this shunt, this pathway? It's kind of interest or relevance. What's the kind of an unfortunate consequence of it?
Does it use an ATP?
Yes, basically, yeah, that's exactly right. So you can see this is the normal pathway. It's phosphoglycerate kinase. That's the standard pathway through glycolysis. And that's one of the key steps where you're regaining an ATP that contributes to the ATP output. And so this is what's called a futile cycle. So it kind of, I'm not sure exactly how it unfolded in the history of it, but a futile cycle is doing something that seems wasteful. And so it's, normally we're so precious about ATP. The fact that there's this process going on in red blood cells or in the body suggests that there's some importance in it, that it's prepared to lose an ATP in the process. So you can see here that there's been all that phosphorylation that's happened earlier and that phosphate is lost in this pathway, but it's lost just as a free phosphate. It's not being incorporated into an ATP molecule. So in red blood cells, where you're producing the D3-DPG, you're actually sacrificing ATP in order to do that. So I'm not sure, it may actually be in practice a very small quantity of ATP that's wasted in order to produce enough 2,3-DPG to have the physiologic effect that it needed. So it may not actually be that relevant, but it's just kind of a point of interest of the existence of this futile cycle. Okay, so that's kind of glycolysis in a nutshell. Any questions on that before we move on to the next one? Okay, gluconeogenesis. So yes, someone mentioned that already. Yeah, kind of need to know a bit about this. Yeah, so what can you tell me? What is it, for starters? Sian, did you want to have a crack at this one? No, maybe she's off having a coffee break still. Anyone else?
This is the production of glucose from amino acids or lipids. I think pyruvate gets converted to glucose.
Yes, that's pretty much it in a nutshell. So yes, we talked about glycolysis, where you start off with glucose and you end up with pyruvate, and kind of pyruvate now going back to glucose. So how does it differ from glycolysis? Is it just the same reactions in reverse?
It's a different enzyme pathway.
Right, yes. So, and so where does gluconeogenesis occur?
Primarily in the liver. I think there's a little bit in the kidneys too.
Right, yeah. And so why doesn't it happen elsewhere or everywhere in the body?
I presume those enzymes are specific to the liver and the kidney.
Yeah, so kind of like we said with the red blood cell, where it's got the specific expression of the enzymes to produce the D3-DPG, the liver and the kidneys have the enzymes necessary to produce it. And so this is a slide kind of, I guess, highlighting those differences in enzymes. So this is kind of the usual kind of pathway going down through glycolysis this way. So these are the key enzymes. And so these are the, I think I've got it on the next slide actually. These are those kind of unidirectional irreversible reactions that occur in glycolysis with those enzymes. And then these are and actually, yeah, so this is to pyruvate. And then this is actually the Krebs cycle here with oxaloacetate in there. So this is how it kind of, in the liver and kidney, gets back into glucose. So it has to go through oxaloacetate and then up there. And then so there's some of those enzyme pathways are common to both glycolysis and gluconeogenesis, but for the full gluconeogenesis, you need these specific extra enzymes here. And that, again, that's those, yeah, so those ones, these single directional red arrows, where these black ones are common to both glycolysis and gluconeogenesis. And I'll just go back a second.
I'm not sure if you're going to... Oh,
go on, yep. No.
Yeah, quick question. I'm not sure if you're going to come to it, but I get really confused. Do ketones come from fats or proteins?
No, that's a very good question. We'll get to that very shortly, so hold on to that one. While I'm here, though, actually we are a bit pushed for time. Sorry. Yes. So this first step here. So I'm trying to work out how I can avoid this being a game of guess what I'm thinking. So yeah, just first up, just describe what's happening in this first step here. I hope you can see my arrow. So going from glucose to glucose 6-phosphate. So what's happened in the process there? And does anyone know what the importance of that process is? Ben, what do you make of it?
Ed's suggesting the add a phosphate.
Yep. So what's the significance of that in a very broad context?
Oh, it makes it less lipid soluble.
Yes, yes. And what's the importance
So
of
that
that?
means that you can't go through go past membranes, go out.
Yes, that's right. So we're inside the cell here. We've got glucose. So how's the glucose got into the cell?
So if this is muscle, would be via GLUT4 transporter within.
Yeah. Yeah. So it's generally moves down through a glucose transporter across the membrane. But yes, once it's kind of got that phosphate attached, it can't go through those GLUT transporters anymore. And so the key thing here is that this, in most tissues, this phosphorylation is irreversible. So once you've gone through this hexokinase, you've got the phosphate group added. It can't go out through the GLUT transporters. It can't get across the membrane at all. So it's now kind of locked in the cell. So this commits that glucose molecule to staying in that cell. Now, it might go down glycolysis. It could be used for something else, depending on the cell. But yes, this is an important thing that will come up in a couple of places in this tube and probably even in my next one as well. So that's an important thing to remember, that this initial step is irreversible and results at locking the glucose into that cell. Okay, so yes, we've started talking about this a little bit briefly. So the citric acid cycle, Krebs cycle, whatever you want to call it. Someone want to have a crack at talking about that? Tell me what you know about it. I don't think you need to know too much detail about it, but there's a couple of key things, I guess.
In the citric acid cycle, we consume carbon dioxide and produce a small amount of ATP, but the key role is to produce 6 of the NADH plus and the FADH plus, which can be used in the electron transfer chain.
Yep. At the beginning there, you said consume CO2.
Yes, sorry.
So yes, yeah. So it's yeah, you're pretty much spot on, and the next slide kind of shows that. So yes, we kind of got the pyruvate that we talked about, 3 carbon molecule there. That's come from, well, it can come from a number of places, but particularly glycolysis was what we're interested in. And then it goes through this citric acid cycle. This is the oxaloacetate that we kind of talked about briefly for gluconeogenesis. So it's one of the intermediaries in the citric acid cycle. And really that's how yeah, pyruvate ends up getting back into glucose. So it's not the pyruvate itself necessarily going back up the pathway. It goes through citric acid cycle, and then it's the oxaloacetate, I gather, that goes into gluconeogenesis. And yes, to mention, so yes, this is the first place where so glycolysis, there's no loss of carbon, there's no CO2 produced in glycolysis. This is the first place where you lose any CO2, that pyruvate to acetyl-CoA. And again, this is an irreversible reaction as well. So this is another key regulatory step, that commitment of pyruvate to acetyl-CoA and the citric acid cycle. And again, yeah, this is where that important molecule of acetyl-CoA comes in. So as it goes round, spits out the NADH that you mentioned, some more CO2 coming off here and here, and the FADH2, more NADH. So these electron kind of donors, I guess. These are really the heavy lifters in terms of producing ATP through oxidative phosphorylation. So while you get a bit of ATP and a bit of NADH from glycolysis, this is where all the big money is. And it itself produces some GTP, which is interesting. It's not ATP, but they're pretty much directly, there's an enzyme that can swap GTP to ATP. So this production of GTP is effectively production of ATP. But I guess they could trick you on a MCQ question if they asked you about what does a citric acid cycle produce, and they could trip you up on GTP versus ATP. That's all pretty fine print stuff. But yeah, the main things is that the citric acid cycle is a big producer of NADH, and it's also where all the CO2 comes from. So after this step, yes, there's kind of no more CO2 loss. So I think And sometimes they'll ask questions about what the ultimate output of glucose molecule is if it goes through glycolysis and the Krebs cycle. I think it gets a bit complicated because you need to factor in what the NADH and all that stuff. Oh no, that's in terms of ATP. If you're just talking about the net sum of one glucose going through glycolysis and the citric acid cycle, then I think it's 8 NADH, 2 FADH, 2 GTPs, and 6 carbon dioxides is the output. Remembering that, yes, the glucose gets split into 2 pyruvate. If you then want to work out how much ATP produces, that gets complicated because you need to factor in the oxidative phosphorylation, which is less stoichiometric in that sense. That's pretty much it. And yeah, so the next one, amino acids. So yes, asked a question about that. And this is kind of where they feed in. So it's a very colorful and busy diagram, but it's basically this color-coded legend in the beginning. So they talk about amino acids as being glucogenic, ketogenic, or both. And basically what that means is, so if they're the glucogenic ones are ones that kind of feed into either pyruvate and or the citric acid cycle. And so they can ultimately be turned back into glucose via gluconeogenesis, or part of them can. So it's part of the amino acid that has a carbon backbone that can be turned into that. And then there's some that'll have usually part of the side chain, I think from memory. It can be, they're kind of ketogenic, so they can be broken down into ketone bodies, which we'll kind of get to in a little bit. And then there's some that can do both, like different parts of the amino acid or whatever can be used in different ways, depending on what the dietary or the energy demands are, what we're short on or what we're overloaded with in any given situation. So it's a busy slide, but it's not a bad description of where the different amino acids, you don't need to know, I don't think so anyway, which amino acids do which, but you just need to know that there's some that are glucogenic, some that are ketogenic, and some that can do both potentially in terms of their metabolic function. Okay. Oh, sorry. And again, yeah, again, acetyl-CoA is another key point in here for all these, particularly the ketogenic ones to go into, because yeah, we'll come to, actually, I think after the next one. So yeah, beta oxidation, which someone mentioned. So that's the breakdown of free fatty acids. So again, pretty fine print stuff here. Less, I think this is even finer print than the glycolysis and citric acid stuff. But the main things are that, yes, you get a free fatty acid. Again, it's bound to CoA. It's not acetyl-CoA. It's like acyl is just a generic term for any kind of carbon chain like this. And so it starts off with the free fatty acid. There's the coenzyme A is joined to it, and then it enters this beta oxidation cycle, and the beta refers to it, the beta carbon of the fatty acid is what gets hydrolyzed or oxidated, I can't remember which, yeah, oxidated to at the end. And so it goes through, water's added, there's some NADH produced here again, so that's another source of NADH for the oxidative phosphorylation, and then an acetyl-CoA molecule is spat off at the end. So the main thing here is that beta oxidation is another source of acetyl-CoA to go back into that diagram there. And then depending on the length of the fatty acid, it will go through this cycle multiple times, and each time 2 carbon atoms being chopped off to go back through the cycle. And then, yeah, there'll be different steps depending on whether it's a saturated or unsaturated fatty acid, but again, that's this super fine print. So yeah, the 2 main take-home points are that it produces acetyl-CoA, starts with fatty acid, produces acetyl-CoA, and produces some NADH along the way. Okay, and now, yes, onto oxidative phosphorylation. And so yes, this is kind of where all the money is, so to speak. What can you tell me about this process? Who wants to have a crack at that? What's it involve? Ben, you online?
Very good.
Yeah, could you repeat the question? Sorry.
Oxidative phosphorylation. What can you tell me about the process involved in that, or what are the steps?
So you have transfer of electrons to the electron transport chain through your electron carriers, so NADH and NADH2+2.
Yep.
And that establishes a electromotive force through the inner mitochondrial membrane. And the electrons get passed through a certain number of carrier proteins. I think there's 4 cytochromes, I think they're called, and the last one being a particular name called ATP synthase, which couples the transfer of electrons and the movement of hydrogen ions in order to produce ATP.
That's very well described. Straight off your study notes, I'm guessing. Yeah, no, that's yes, very good summary. That's wherever you got that from. That's spot on. So yes, we've got all these electron carriers that have come from multiple sources along the way, as we've just seen, and this is kind of the key area where the magic happens. And so yes, the electron transport chain. Yes, there's various enzymes involved. This is all going on in the mitochondria. We get the NADH coming along here, donates the electron to the transport chain, which then skips its way along. And as part of that process, these hydrogen ions get pumped into so this is actually the intracellular membrane. So if you remember, the mitochondria have these 2 plasma membrane layers that are kind of close opposition, and then it's in between those 2 that this high concentration of hydrogen ions happens. And also, yes, this is finally where the O2 gets consumed and that water gets produced. So kind of right back what we started talking about in the days of Lavoisier and Mayo, the stuff that they were discovering was kind of the CO2 that we talked about in the citric acid cycle, and the oxygen being consumed here as well. And yeah, the interesting side point is that for a long time, I assumed that the oxygen that we breathed in got turned into carbon dioxide that we breathed out, but that's not actually the case. So it's the oxygen in CO2 is, I guess, comes from a different source than it's not the oxygen that we breathe in. That's just a side point of interest. And then yes, that electrochemical gradient for the hydrogen ions then goes back through the ATP synthase to produce the ATP that we're interested in. Now, this is, the key thing here is that in order for this to happen, you need ADP. So that's one of the substrates to produce the ATP, obviously. And you get the ADP from using ATP. So at this point, you can see this idea of what they call coupling. So if you're not using ATP, then the ADP will become low, and so you'll stop needing to produce ATP. So then the hydrogen ions will no longer be coming back through the membrane here, and so the concentration here will just build up higher and higher to the point where the electron transport chain stops working, and so that means that the NADH can no longer donate its electron here, and instead of going back to NAD+, you just left with too much NADH. And this is where it then backs up into the citric acid cycle, and yes, potentially even back up into glycolysis. And now, a bit of a tangent to this, but a relevant one that will eventually come back to what we're talking about here is this imaging here. So can anyone recognize what type of medical imaging this is showing?
Bill says it's a PET scan. Sorry.
A PET scan. Yep. So what can you tell me about a PET scan? What's the physics that's involved?
So it involves a radio tagged isotope being either ingested or injected, and then the concentrations of that radioisotope create hotspots where it's taken up.
Yep, that's pretty much it. Do you know what PET stands for?
Positron emission technology.
Yeah, so it's a positron scanner. That's what it's measuring. So the radioactive decay of whatever the tracer is, it emits positrons that then get measured with the camera. I have a long and complicated medical history, which some of you may or may not know. So I've had a few PET scans in recent years, and this was the preparation, part of the preparation instructions for my PET scan. And there's a few interesting things there, but the main one I wanted to highlight here was this bit circled in red. So part of it was that during the colder winter months, please dress warmly for 48 hours prior to your scan. And this will ensure we obtain the best quality images. Now, I think I might have put this in the wrong order. Yeah, so I guess, yes, let's discuss this for the moment. So what do you think might be the rationale for that instructions prior to having a PET scan done?
So you can, your brown fat will produce heat, non-shivering thermogenesis, which will distort the image.
Right. Yes. No. That's very good. You've jumped straight to the chase there. So yes, and it kind of comes back. Yeah. So I guess kind of someone mentioned before the tracer that's injected. What do you know about the tracer that is kind of primarily used for PET scans?
Tagged glucose.
Sorry?
Tagged glucose.
Tagged glucose. And do you know what it's tagged with?
No.
Okay. Yep. No. Well, that's and this is
Magnesium?
No. So that is definitely used in radiopharmaceuticals, but not in this particular. Well, not in this particular PET scan. It might be other PET scans.
Carbon-14 or?
No. There is radioactive carbon. I'm not sure if that's used in radiopharmaceuticals, but it's certainly used in that's in carbon dating of kind of ancient artifacts and that sort of thing. I'm sorry, I suspect it may not be radioactive enough for kind of the rapid scanning things, but I think technetium does get used. But the one that's used for the scans I had anyway, and particularly when you're thinking about metabolism of cancer cells, which is often what PET scans are used for. So yes, it's a radioactive glucose, and it's actually tagged with radioactive fluoride. So even though we do call it radioactive glucose, it's technically not glucose anymore because we've removed an OH group and replaced it with a fluoride. Yes, the technical name for it is this 2-deoxy glucose. Now, it's going back to what we were talking about before about it entering cells. So this form of glucose, it enters cells. It gets phosphorylated by the hexokinase that we talked about before. But because of the fluoride substitution, it can no longer go down the rest of glycolysis. So it gets locked inside metabolically active cells that are actively taking up glucose, but it then hangs around there and doesn't end up going anywhere else. And so it's giving off its positron while stuck inside cells that are actively using glucose, and of particular interest are cancer cells that are very high users of glucose and they use glycolysis a lot more than they use some of the other metabolic processes. So that's kind of the basis for it. And then, yes, as already mentioned, if someone has been exposed to cold, then that can activate their brown fat. And it was actually the interesting historical thing here was that I'm not sure what you've learnt for your exams, but generally they'll speak about brown fat being present in neonates, but certainly some things I've read that mention it's not in adults. But it was actually CAT scans when they came on the process that they found that there was these consistent artifacts appearing in the scans in these distributions. So kind of around the shoulder blades, the scapulas, the central spine, and around the kidneys that were showing these artifacts. And this, they eventually able to work out that this proved that adults have brown fat, not just neonates. So that was not until CAT scans came along that they were able to kind of pretty conclusively prove that brown fat was in adults and not just neonates. And I think there's the next slide. Yeah, so you can see on the left here, in a warm environment, that's what the PET scan looks like, but then put them in a cold environment for a little bit and it starts to activate their brown fat. And then the next slide shows it even more. So in a thermoneutral environment, in a cold environment, and then so I think the cold environment was 16 degrees Celsius for 2 hours. That alone was enough to activate some brown fat. But then when they were exposed to that for 6 hours a day for 10 consecutive days, you can see it kind of upregulated the production of brown fat. So there was not just did the brown fat become active, there was more of it when you get kind of acclimatized to the cold. So that's just an interesting historical process of how this brown fat in adults came to be kind of somewhat surreptitiously discovered. And this is the other thing on my scan preparation. So yes, do not perform any strenuous exercise for 48 hours prior to your appointment. And so there's some parallels here between having a PET scan done and measuring your basal metabolic rate, because if they're looking for cancers, they don't want other things interfering with a scan. They want to see the metabolically active areas that are likely to be cancer. So they want as much of your body to otherwise be at rest. And so you can see back here, the brain's, it's metabolically active no matter what, as I'm sure you're aware. But yes, they want you, and so that thing about no strenuous exercise, that was a similar criteria for basal metabolic rate as well. So it's relevant here. So I had no problem avoiding strenuous exercise. Interestingly, I was allowed black coffee. So they wanted you fasting, but they didn't have the same strict regulations about caffeine, fortunately. No smoking, though, was interesting. But then, there was this interesting one about not chewing gum for 24 hours prior to your appointment. And so I asked them about that. And yeah, apparently even that you can get an artifact in your masseter muscle from chewing gum. It's like that repetitive exercise that we're doing with our masseters can still be picked up on a PET scan kind of 24 hours later. And so yes, that's the analogy to the basal metabolic rate testing. So, sorry, but yeah, we've gone over the 2 hours now. So yes, if you need to drop out and go into other stuff, back to work, whatever, I'm sorry, but yes, the recording will be available, but I'm happy to crack on. I don't think there'll be too much longer at this point. So yes, this is showing brown fat and kind of, I guess, the standard white fat. And what's the, I guess, histological difference? What's the reason that brown fat looks brown and white fat looks white?
Could I just jump in, Reece, just before other regs drop offline?
Yes, yes.
There's a reg, one of the ATs is staying back to do a Viva practice. If anyone wants to stay online, we can record it with this Zoom session. All right,
okay. Sounds good. Actually, yes, I should look into the primary Viva stuff as well at some point. Not this evening, sorry, but at some point. Yes, okay, yeah, so back to the brown fat, white fat. Can anyone explain why they look so different?
Got a density of mitochondria in the brown fat.
Yeah, that's exactly right. So yes, this next diagram, stylized version of it. Yeah, so I guess yeah, as you can see there, all the mitochondria, and it's much less lipid stored there as a result. So yeah, so what's the mechanism of action? How does this brown fat actually work? What does it do?
It uncouples the oxidative phosphorylation in the electron transport chain, so that energy is produced as heat rather than as energy, I guess. That doesn't make sense, but yeah, you get heat produced rather than ATP.
ATP, yes, that's the key. Yeah, no, you're spot on there. So yeah, going back to this diagram before, so as I said, so in this diagram, you kind of, if you're not doing exercise, not using ADP, if you're not using ATP, then you run out of ADP, and it all kind of backs up here, and this concentration up here gets so high that it kind of, everything clogs up backstream of that. Whereas the, so in brown fat has a thing called an uncoupling protein. I think there's like 3 different isoforms of it. It's also called thermogenin. And I think it's kind of goes across this membrane in a similar fashion to like a transmembrane protein in a similar fashion to the ATP synthase. But it can transport hydrogen ions back across the membrane but without having this necessary step of producing ATP. So you don't need ADP, you don't need free ADP here in order to for the uncoupling proteins to work. So they just dissipate this hydrogen ion gradient. So that means things can keep donating these electrons here, and the NADH gets recycled. And remember, we said before that metabolism, all these chemical processes are inefficient. They will always produce heat. So it doesn't necessarily need to be the usage of ATP that's generating heat. It's just every single chemical reaction along this pathway will produce a small amount of heat. So as long as you can keep all these other processes going, you're going to get heat, and you just don't need that final step of the ATP usage. And then that keeps the glycolysis, the citric acid cycle going, the glycolysis going, the beta oxidation, whatever your source of alternate energy is. You can do it without needing the ATP synthase step. And yeah, I think I've covered those other bits all right. And this is probably another example of a futile cycle because, yeah, we emphasized before the importance of ATP. So any process that kind of avoids the production of ATP when it could have otherwise done it, you've got to assume there's some important point to it, because ATP is so important that if you're going to waste the energy, it must be going to something useful. So in red blood cells, you waste the ATP to produce 2,3-DPG. In brown fat, you waste or avoid producing ATP in order to produce heat in those kind of situations. Any questions about that? Brown fat. And yes, non-shivering thermogenesis. So yes, it's the idea of producing heat, but without needing muscular activity to do so. And in the interest of time, we might kind of skip along to lactate. So I think there is one of the learning objectives in the syllabus that I sat under was kind of, yeah, the role of lactate and how that's produced. So what can you tell me about lactate? When is it produced and what happens to it?
So lactate is produced in the anaerobic setting. The role of it is to recycle the NADH produced into NAD so that glycolysis can keep cycling around to produce those 2 ATP. Yep,
that's pretty much it. And then, yeah, so what ends up happening to the lactate?
The lactate can go into the Cori cycle where it can get converted back to glucose.
Yeah, that's pretty much it in a nutshell. So yeah, this is a very simplified diagram of the processes involved. Obviously, yes, with oxygen, ATP don't actually come off the Krebs cycle like that. But yes, it's basically just showing the Cori cycle up here. So glucose going down into pyruvate. And then, yes, if you've got oxygen down here, ultimately, then it can continue on down there. But if you move out this step, as we showed, it backs up to here to keep glycolysis going. You need that NAD back. That can happen through this step, which I think the next slide shows it a bit more in detail. Then usually in the liver is where the Cori cycle happens. It gets reconverted back into pyruvate. And I think on the next slide, so yes, it's not very high resolution. I couldn't find a better one than this. But this shows, for example, in a muscle, but it can really happen in any tissue. Glucose, glycolysis, pyruvate, and then, yes, this NADH being used up to produce NADH, a lactate, and then has to go through the blood to the liver for that lactate. So the lactate dehydrogenase enzyme is the key one, and there's different isoforms of it, and it's at a one that's reversible depending on context and concentration gradients. And so that's where it gets converted back into pyruvate, can then go up gluconeogenesis as one option and back into glucose. So it's kind of this Cori cycle of involving glucose, lactate, pyruvate, and so on. And I guess as a side question related to that, what happens to with the lactate that's as part of Hartmann's solution? Anaesthetists love using Hartmann's, or lactated ringers as it's sometimes called. So what happens to the lactate that is part of that solution? Is it going to cause lactic acidosis?
No, it turns into bicarb.
Yeah, that's an important point. So it itself can, can get metabolized in a few different ways. So one of it is going back to pyruvate, but the important thing to remember with the lactate that we give in Hartmann's is that it's not actually lactic acid. It's the base form. It's the free base, and so it's actually going to have the opposite effect. If anything, it's going to act as alkalizing the blood in terms of pH. It's only going to be a small effect, but it's certainly not going to cause lactic acidosis. But what will stuff up is any measurements of lactate that are taken immediately after administration of a large volume. I think some of the stuff that I saw can have a significant impact on plasma lactate for maybe 15, 20 minutes afterwards, but it's certainly something you need to take into account when measuring the lactate. But I remember early on being concerned about it causing lactic acidosis until it was pointed out to me that no, it's not an acid, it's the base form, and that its ultimate fate is back into bicarb or some other metabolic process, again, usually within the liver. Okay, and then, so this is kind of a summary slide, my hand-drawn one that is, I keep meaning to put it into a more readable graphic form, but that again shows that central role of acetyl-CoA feeding into all these things. So beta oxidation here ending up as acetyl-CoA, acetyl going into the tricyclic acid cycle or Krebs cycle. Acetyl-CoA is used for formation of cholesterol, ketone bodies, which we haven't really gone into much today, unfortunately. Acetylcholine is another key component there that we do need to know about. And then, this is the pyruvate lactate Cori cycle side of thing, and glucose here, do 3-DPG. So this is a very basic summary of all the metabolism we've talked about, and then the coupling, decoupling, thermogenin is another name for the uncoupling protein in brown fat. So that'll be in the slides that get sent out. And then I think the last topic we've got is starvation, or as anaesthetists like to call it, fasting. And again, this is from my own medical history here. These are my own bloods from a number of years back. And so have a look through them, and can imagine being handed this in a Viva and asked to comment on the blood results that you see. What are some things that stick out to you?
So we can see that your phosphate and your potassium are low, suggesting that you've had a deficiency of energy, and you'd be at risk of refeeding if we fed you lots of glucose and you rapidly, your insulin also forced your potassium intracellularly, and your phosphate, you wouldn't have much of an ATP reserve, so it would drop further. Your albumin's low and you're malnourished. Yeah,
so for a bit of context, this was after second laparotomy in the space of a couple of months. And yes, I was horribly malnourished and underweight. And you've kind of picked up the key things there. So yes, the urea is very low, the creatinine's a bit low. So there's all the markers there of malnutrition. And then yes, you've kind of picked up the key points there that I think is in that syllabus page from when I sat it about refeeding syndrome, and you've kind of picked up things there. So, and I guess the other side of things is the relevant for the primary. What can you tell me about the full blood count?
Pancytopenia.
Yes, and what?
Very low hematocrit, suggesting widespread myelosuppression.
I guess is it a pancytopenia?
No.
Microcytic hypochromic anemia.
Yeah. So what's that tend to indicate?
The iron deficiency.
Yeah. So it fits into this malnutrition product. So yes, I'm kind of low on iron. Seems to be low protein reflected in the urea and creatinine. The electrolytes are out of whack, and that's kind of multifactorial. It may not necessarily be a deficient, like a lack of intake of those electrolytes necessarily, because they're kind of, you get flux between the internal and extracellular environment. which can complicate the measurements, because remembering these are just the plasma things. But yes, someone mentioned their refeeding syndrome. So what can you tell me about that? What are the issues and how do we manage it or prevent it?
The issue is if we give you lots of glucose, you'll release lots of insulin, and that'll drive your potassium lower further, and it will utilize phosphate to produce ATP, which will drop that even further. So you have to aggressively replace your potassium and your phosphate. Your magnesium will also, I think, drop. Yes, yeah, that's pretty much correct. And yeah, you mentioned the insulin and glucose there, but it's not limited to glucose or carbohydrates. Pretty much any caloric intake, any kind of, whether it's fats, protein or carbohydrate, could trigger refeeding syndrome, because they can all have an effect on insulin, and even not just the insulin response as well. It's those electrolytes that you mentioned, so particularly potassium, magnesium and calcium. Once you introduce calories back into the system, or those metabolic processes that we've just talked about kick into action. And so yes, the magnesium is a very common cofactor for a lot of the enzymes that are involved in those processes. So it'll be needed. Yes, potassium gets driven intracellularly, and yes, so you're trying to work out, yes, this is where it gets complicated with DKA as well, whether there's a whole body deficit of potassium, possibly, even if the plasma values aren't too bad, which can complicate things. And so, yes, the concern is that all these things that have a key role intracellularly, they will rush inside the cell out of the plasma. So in particular, potassium, magnesium, and calcium. And so what's the concern there if all of a sudden your plasma concentration of those three electrolytes drop with the reinstitution of feeding? Bill says you'll get a ventricular arrhythmia.
Yep, that's definitely one. So yeah, what does that? Well, pretty much all of them could have a role in that. Yeah, so that's the concern. Yeah, kind of cardiac abnormalities and yeah, muscle issues and those sorts of things. So that's the concern. So yes, I'm sure if you spent any time in ICU and that sort of thing with TPN and the dietitians, they're kind of big on measuring all these electrolytes and stuff. And so yes, I was keen to get back on TPN, but the dietitians wouldn't let me until I had my electrolytes sorted out. So I was on solely on electrolyte replacement for a few days, and then the values normalized, and I was able to start TPN at this point. So yeah, I think that is something that is kind of clinically relevant in the context of this nutrition and metabolism topic, and something you could get asked on in an exam, given that, yeah, there's some overlap with not only ICU, but also, yeah, fasting for surgery and repeated surgeries. So this is kind of my situation where there were other issues related to the immunotherapy that I was on, but a lot of it was 2 operations and difficulty with keeping food down, which is not an uncommon situation that we see in patients on return trips to theatre. So it's definitely something that we need to be aware of. Not that we're likely to start feeding patients, but it might be relevant for kind of, yes, if we're kind of giving them too much caloric load through other means, and may need to avoid glucose solutions and those sorts of things. And then this is from Ganong, I think, again, which is a pretty good summary of some of the processes involved over the longer term with malnutrition or starvation. And so again, given this was, I'm assuming this is still part of the syllabus from when I sat it. It's a pretty complicated diagram, but it goes through the steps pretty quickly. I don't think you need to remember it off by heart, but given it's in Ganong, it's probably not a bad reference to go back to, and then you can make your own flashcards or summary statements of the implications and processes involved in malnutrition and starvation. And then I guess the fine print, I think there is actually something in the old syllabus anyway about the process of TPN. And again, this is another thing that the ICU dietitians will often ask you to do, is to ask for blood tests on some of these very minor minerals trace elements. So this is, again, from Ganong, one of the recommended texts that might be relevant. And so, yes, I'll finish with my summary slide that I started with. That's pretty much it for today. Sorry, I've gone over time yet again. Happy to take questions now, or you can email me. Otherwise, that'll be it, and I'll let you get to your Viva practice. Any questions?
That was great. Thanks very much.
Yep. Okay. Well, yeah. If any occur to you or whatever, just shoot me an email, and yes, I'll try and look into the Viva. So that's all happening via Zoom, is it? By the sounds of it.
I was thinking I can just leave this conference going if any of the other edges are going to.
Yeah. Yes. But yeah, kind of over the next number of weeks or whatever, are there kind of regular Zoom sessions booked?
Fantastic.
I'm trying to work out, what's the process at the moment, because with all the COVID stuff.
Thanks, Reece. So I know that Alison Clark has sent an email around to the consultants and some of the regs. She's trying to line up through either Zoom or through Microsoft Teams a calendar where people flag the dates that they'll be doing it.
Yep. Okay. Well, I'll have a look at my calendar, and yes, I've been able to help out sometimes in the past. So yeah, it'd be good to be able to do that again. So I'll look into that.
Thank you.
Great. Okay. Well, I'll leave you to it then, and I'll work out how to. Well, stop sharing for starters, and then I will leave it, and I'll catch up with you later. Okay. Bye.
Thank you, Reece.
Thanks, Reece. Yeah.
Are any of the regs going to stay on? Completely up to you.
I'm going to be checking out, but see who. I'll try and keep this meeting open if I can. But if not, you might have to. If I leave, you might have to log back in. But it will still remain open. You just I might have to end it, and then for the recording's sake, and then you can just come back in whenever.
All right. Anyone who's staying in, say so. Otherwise, I'll just turn it off and do it face to face.
Yeah, Dan, I'm going to go and make some dinner, but do you mind writing down the questions you do?
Yeah, glory.
I've decided 1st of September I'm going to start